get on today. All right, let's see where we are. All right, so engine performance, we're going to look at thermal efficiency and propulsive efficiency. It's possible to measure each part of the engine turn, find out where it's performing, etc. But we can break it down into specific efficiencies. Okay, we spoke about back in the first few days about compressor efficiency, isothermal, adiabatic being ideal, where if there's too much heat loss through casings, we're not as efficient as certain other ones. Certainly with a centrifugal compressor, it's not quite as efficient as a natural flow compressor. The natural flow compressor has modular sort of status of pressure rise through each stage, where a centrifugal one is one big pressure rise, a lot of heat, and a lot of heat gets lost as well. So again, depending on the build of the engine, the type of engine, and the materials used, can all benefit to where we are. 100% would be great, but we never get 100% efficiency, unfortunately. So we'll look at a breakdown of what's called thermal efficiency, to do the heat, and propulsive efficiency, to do with thrust and that sort of thing. So thermal efficiency, heat produced by the fuel compared to kinetic energy in the gas stream. Into indicated thermal efficiency, okay, and brake thermal efficiency. Okay, so indicated thermal efficiency, and it's got indicated, that's the theoretical thermal efficiency of what would be that of the actual engine. Okay, the brake is what's left, so we'll speak into that. Oops. Thermal efficiency and brake thermal efficiency. All right, so let's say indicated, engine will be produced, and in theory, that's the type of heat energy that should be not lost. Okay, so basically kinetic energy passed at the gas stream as a result of the fuel burning. Ideally, we would get 100% of that energy all the way back out, but unfortunately, we don't. Again, it's a simplification of it. Indicated efficiency assumes there's no mechanical losses, but the brake thermal efficiency is using the work rate on the engine less the losses through things like friction. If you've got friction, you've got heat. If you've got heat, then you've got loss. So we're not getting all that heat energy going through. So basically, brake thermal efficiency comparison between the heat obtained from the fuel and the velocity of the gases leaving the engine. So indicated, ideally, what's going in and out. Once you've burnt the fuel, brake is actually what you've got left once they take things like friction and all that sort of stuff out. Okay. Propulsive efficiency is power derived from the change from kinetic energy in the gas stream to the thrust power it produces. And that's just if you can't sleep at night, there's a little formula for you. Velocity inlet, velocity exit. Okay, what goes in, what comes out, and how effective it is. Now, a jet engine is more effective the faster it's going. It doesn't like to be sat still. It likes to be going faster. Once you get ram effect and all that sort of thing, so that's when we get our best propulsive. Not the thrust efficiency, but propulsive efficiency. Okay. At speeds below 400 miles per hour, it's far more efficient to use a propeller. Okay. Propeller takes a large amount of air, small velocity. As I saw before, a jet engine takes a small amount of air and a large velocity. But it's far more efficient, high level, and going faster than it is at lower, slower speeds. Okay. So basically, propulsive efficiency is a comparison between the useful power derived from the change in kinetic energy of the gas and the thrust power obtained from it. All right. And just get on that part there. There's also, again, you also get some waste from propelling mechanism, much is dissipated into the exhaust gas stream. So at lower speeds, the pure jet stream wastes a lot of more energy than a propeller because of the higher exit velocities. So as the aircraft speed increases, you get a better ram effect, as I said before, so we can match the force going through the engine on the surrounding air. So that's that one. Here's a typical example of the graph we've got between prop fans, bypasses, and pure jets and turboprops. Okay, speed along the bottom here, we'll range up to about 1,000 miles an hour, and propulsive efficiency going up. So if we look at, we've got a prop fan here. Yeah, it's quite low, so quite high, say, at low speeds. We've got efficiency, it's getting quite high bypass, because a high bypass engine is basically almost a propeller engine, but with a casing around it. Hence why it's quite efficient. Oh, back in there. Okay, so you can see at low speeds, actually a turbo fan or high bypass isn't too bad. It's when we get down to more like a pure jet type thing. So a pure jet turbojet is more efficient the faster it's going. But overall, jet engines need to be going faster. Okay, so this one here, the high bypass. Then we've got the low bypass, which becomes more of a pure jet sort of thing. Then you get the bypass ones as well. So high bypass is not too bad. The prop fan, and then a turboprop, yeah, it's very efficient at low speeds, but as it gets faster, well, that big propeller starts to act as a drag. Okay, so it won't get to a certain speed before the propeller itself is just becoming a big drag component. So it drops off, peaks quite quickly, up to 400 miles an hour, but then drops off rapidly the faster the aircraft goes. To the point, it won't become as efficient at all. A nice pure jet, simple jet, quite linear all the way through, but it much prefers going faster. With ram effect, so that's just typical sort of comparison there. So if you get a question exam, say which type of aircraft would be more suitable for lower speeds, propeller type aircraft. Yeah. Or likewise to say what's the more efficient at high speeds, a jet engine. Engine thrust indicators. Yeah, we've got, as I saw before, we've got thrust going forward and backwards. Remember, thrust produced by a gas steam engine is felt in all static and rotating components. So again, early indication was just an RPM gauge, but that didn't provide any evidence of thrust. All it told us was how fast these spools were going. Now in this case, we've got a single spool here. So that would just tell how fast it's going, which is like, okay, you can have a fast moving engine, but with a low amount of thrust, depending on the conditions it's in. So as a more accurate measurement to allow the pilot to know how much thrust he's got, because let's say we've got the same engine running at the same RPM on a cold day, the same engine running the same RPM on a hot day, you won't get as much thrust. You need to get more ram air in because the hot air in the front. So again, if you're getting towards like a mountain and you need more thrust, you might see the speed of the engine. That might necessarily give you the right amount of thrust. Okay, an indication of it at least. Is it back in now? Where's my mouse going? Okay, another one coming in. Right, so again, you can also have thrust is felt, or acceleration, say, can be rearward as well as forward. We get the gas going that way, we also get the pressure thrust going forward as well. So we get rearwards and forward. Hence, we can get, in this case, a total thrust of 11,000 pounds. We've got 41,000 there, 5,000 there, 34 going through, going forward. So overall, we get 11,000 pounds of thrust, just as a general setup. Big stuff you might not see this very well. It's an example taken from the book, if I remember right. Where are they? Yeah, you might. This was an example we've got in the book on page 92, I think it is, on my book. It might be. It's the same one we've got in your old books. So you might see it in one of your old books. And what we've been given is a general. It's the same one, yeah. I think we just put it into the new book as well. So CF6 engine, it uses 800 kilograms a second of air mass flow, and that gives a thrust about 273 kilonewtons, so quite a powerful engine. So the specific thrust for this one will be just 273 over the mass flow, which is 273 divided by 800, or 340 kilograms a second. So that gives you a power of 302.5 kilonewtons at takeoff, using a mass flow of 900 kilograms a second. Again, that'll give you a specific thrust of 336. So it gives you an idea of what the actual thrust is. So that indicates that a G engine, this one here, is producing more thrust at takeoff than this one here. This is a Pratt & Whitney engine. So we've got two engines with two sets of thrust, okay, depending on the mass flow rate. So we can see that the CF6 is slightly more powerful than the Pratt & Whitney. All right. So we've got, as you can see there, the CF6 has got 273 kilonewtons, whereas the Pratt & Whitney develops 302 kilonewtons at takeoff, but it's the mass flow rate that changes it. Yeah, so just because the engine's got a certain amount of thrust, it all depends on the mass flow rate. So that one there uses 800 kilograms a second of mass flow, whereas that's 900 kilograms a second of mass flow. So that needs more air to get that thrust. Excuse me. So dividing that, you can actually see that although there's a bigger kilonewtons of specific thrust, the actual overall thrust is actually less, purely because of the mass flow. Okay. So in this one basically says it can go a slow rate of mass flow, but actually produce more thrust. So it just gives you a little indication there. Okay. Specific fuel consumption. What is that? That's basically how much fuel the engine will burn for pounds of thrust produced. In other words, so the less fuel we burn to get the same amount of thrust, the more efficient that engine will be. Yeah. Best in pounds of fuel per hour, it's over time, or it could also be in kilograms of fuel per hour as well. Again, it just depends on the make of aircraft you got and the indication on the gauge, but usually pounds or kilograms of fuel an hour. Now that helps plan comparing for the operator what type of engine needs to be fitted to the aircraft. Do you need a really massive, huge, powerful engine for a small aircraft, or does a big aircraft need a small engine? How much fuel are we looking to burn for the power to weight ratio and that sort of thing? It all comes down to cost. The more efficient we can make the engines, the less money it will cost to operate them, which means you guys get more money in your wages, yeah, which would be nice. It doesn't work like that, unfortunately. They get more money for themselves. Okay, how much fuel the engine will burn for pounds of thrust produced? We've got an example there. Again, CF56 engine, that'll use 0.611 per cruise. And you've got a V2500 of 0.606. Again, just examples. All right. Pratt & Whitney of 0.565 at cruise. So the Pratt & Whitney is a bit more efficient. That would be 211, like it would be fitted on a 747, about 5.598 at cruise, so a bit more efficient. Some consumption examples. Again, a typical jet is pretty much linear. As the faster it gets, it's pretty much a constant pressure cycle. Okay, so specific fuel consumption tends to be quite linear, the constant pressure. Whereas a turboprop, specific fuel consumption goes down the faster it's going as well. It's using less as well. But the faster the engine's going, then the more fuel you're using. The faster propeller's going, the less fuel it's using. Up to a certain point, but it can't go any faster, obviously. So, very important feature. I guess planning, production, okay, and cost, etc., etc. It says in the notes there, high thermal efficiency requires high pressures, which in practice also means that high turbine entry temperatures. Turboprop engine, the high temperature would result in high jet velocity and consequently lower the propulsive efficiency. So getting a balance of, yes, the core engine of a turboprop has to turn an engine and only produce a small amount of thrust because the turboprop, it's the propeller that provides efficiency. And determine, especially with a turbopropeller, it is the size of the propeller, the weight of the propeller, the aerodynamics of the propeller that makes it more efficient. By using a bypass principle, high thermal and propulsive efficiencies can be effective combined by bypassing proportion of the LP air. In other words, basically turning your fan into a propeller, sort of rough equivalent. Shaft horsepower. Okay, look at shaft horsepower. At knots, again, look at slow speeds up to high speeds, and then actual horsepower we attain as we go up. Now, it is almost linear. You can see a little splurge there, but a certain peak of horsepower will arrive, okay, at sea level conditions, up to a certain speed as well. So we mentioned horsepower, okay, we've got a few ones to look at. Got indicated, now anything with indicated beside it is the theoretical one. So indicated horsepower, strangely enough, will be the theoretical power of an engine if it's completely frictionless. So there's no friction involved. And converting all expanding gas, we've heated the fuel up, we've burnt the fuel, gas coming out in the engine. So that would be the theoretical horsepower of it. Brake horsepower, this is the actual one. So that's a measure of the engine's horsepower before the loss of power caused by things like the gearbox, the drivetrain, maybe a propeller attached to it, anything that causes friction or restraint, that is what is left. So let's say you had an engine that had 400 horsepower indicated, the actual brake horsepower might only be 250, you know, because of things you add to it, which can take off a bit of power or use up a set of energy. And the shaft horsepower, again, is the power delivered to the propeller shafts and the rotors of the helicopter. So you have your indicated horsepower for the actual engine, the time you add the freewheel unit on, the reduction gearing, the rotors and all that sort of thing, that's what's left at the actual shaft. Okay. So that's the three types of horsepower. And it's estimated for indicated horsepower, and the standard figure for losses in the transmission, typical figures are about 10%. So for something about 300 horsepower, you're going to lose about 10%. So you end up a brake horsepower about 270 horsepower. Okay. EPR, IEPR, we should all be happy with that one now, I think. I'll just go check on that. One I didn't put on there was, yeah, sorry, I've done that, sorry. Yeah, EPR and IPR, what was the difference between the two before I put it back up? What's the difference between EPR and IEPR?
Engine pressure ratio.
Yeah. Which is what? What's
integrated engine pressure ratio?
Yeah, that's what they are. So what's the difference between the two of them? We covered this yesterday.
Yeah, engine pressure ratio is the ratio between the exhaust and the inlet. Of
pressure,
the and the
exhaust
integrated.
pressure. Yeah, go on, yeah.
Integrated engine pressure ratio is the pressure between the different shaft or different spool.
Not a different spool, no. This picture gives you a clue.
Bypass and the core engine.
Yeah, so the cold stream, the blue exhaust, the
cold and the hot stream,
and the exhaust pressure. You combine the two together, that gives us a combined exhaust pressure of cold stream and exhaust stream, or cold stream and hot stream, okay? And then both of these over the intake pressure, yeah? So EPR is the exhaust pressure on its own over intake pressure, but IEPR is the cold stream pressure and the exhaust pressure, okay, again over the intake pressure. So there's two things on top, all over the intake pressure. Good. Basically, it's the work done to the air by the engine, the pressure ratio, depending if it's a pure jet, a bypass, or high bypass. So the difference in pressure between exhaust duct pressure and intake, whether it's exhaust on its own or integrated with cold stream and hot stream. And that graph here gives you a rough example of what's going on as well. So the amount of thrust or horsepower that an engine develops is dependent upon the spare energy. It says there that the heat cycle machine has remaining after the cycle has been continued. Now it says there for a line from C to D shows the pressure drop. Okay, so we've got pressure on the bottom as well, pressure in millimeter of the side. So the pressure drop are there, C to D. Okay, so turbine pressure drop, turbojet, we do use a little bit of pressure, although it's a constant pressure system. All right, and the curve from DT is the remaining pressure converted into thrust. Now, from D to F, now that's where it does change a little bit as well. Okay, we can have an additional turbine pressure drop from a turbo propeller, because a turbo propeller can drop it as well. A to B, you get a pressure rise, but going back to the standard PV diagram, so the pressure here, then we get the pressure rise because of the pressure. Yeah. We add the heat, we burn the fuel, we drop a little bit of pressure, and also we're looking at pressure volume. Obviously, volume would expand this way, but we're looking at the pressure drop because we do lose a bit of pressure once we get increasing volume. Okay, so that's just an example of what you might see pressure within the system. Looking at exhaust, if the pressure increased in exhaust is restricting the flow through propelling nozzle, there will be an increase in pressure, and that will give us a pressure thrust at the nozzle here. So why don't we add a divergent nozzle in the back? Normal engines are just a straight duct with a convergent shape that provides a pressure thrust. Okay. If we then add on, well, we can, it's got a condy nozzle. We could turn that side, that could be a rocket as such. It says if for more use, it can be made of pressure exhaust by fitting a nozzle with a condy divergent nozzle. The air leaving the shock wave is choked. Nozzle does not lose all of its pressure energy instantly. The pressure made in the gas is wasted and is dispersed. If we fit a divergent nozzle placed on the convergent nozzle, that will convert the last pressure into useful thrust. But that tends to be less than useful because extra weight, the nozzle gives us extra gained effort required by the aircraft to lift. So you'll tend to find that most aircraft do not have a divergent nozzle attached onto it because at the end of the day, an aircraft's providing lift because of the wings. The faster we can move the aircraft, the more lift. So we need more velocity of gas coming out. Now you could argue that we've got pressure coming out, but if you've got fast gas coming out and then we slow it down to get pressure, then we're going to slow the aircraft down. So it's counterintuitive of that. Whereas if you turn that diagram that way, we now have a rocket. Yeah. So a rocket needs pressure to get, it doesn't need the fast moving gas, it needs pressure to lift a rocket off. So yes, rockets will use a condy nozzle. And once they get enough pressure, off they go. But an aircraft uses wing to provide lift, whereas a rocket doesn't need lift. It just needs pressure. Although they call it lift off, because it's lifting off the base, it's not actually lift it's producing. A rocket doesn't have wings. It might have fins for stabilization, but it certainly doesn't need a lift. So that's why extra weight alone, because the aircraft costs too much weight. So a normal aircraft will just have a convergent nozzle at the end of the exhaust. Okay. So it becomes sonic. Remember, that point becomes sonic. It becomes choked. That way, depending on the size of the nozzle, provide the right amount of choke, which will cause a bit of back pressure, okay, or total head pressure, and that will be the engine is now breathing properly, providing enough velocity at the back end to push the aircraft forward. Right, so just to recap, EPR, exhaust pressure over intake pressure. And IEPR is the cold and hot stream exhaust pressure over intake pressure. Yes, I've not written that in the book. I think the EPR is, I just thought I'd put that up just to make it a bit more easier to understand, hopefully. So EPR is just simply exhaust over intake, where IEPR is the cold and hot stream exhaust pressure, but still over the intake. All right. Everybody happy with EPR and IEPR? Yeah.
Very happy.
Very happy. That's good to hear. You're very happy because it's getting closer to Friday, and Friday's the last day. That just means it's closer to exam. Have you been given a date for exam yet?
27, right after Christmas.
Oh, right. Just what you need. Just after Christmas. Happy Christmas. Have an exam. Have you been given a date for your Module 17 exam yet?
Not yet.
Not yet. Okay. Yeah, the more that drags on, the more you'll forget, especially after Christmas. Oh, well, at least you've got a date for Module 15. That's good. We'll get that hopefully done and dusted. Hopefully you won't have forgotten too much in over a week's time. Right, we're going to look on to controlling the engine as I'm referring to. Yes, we can set an engine up to have so much power, but we tend to design the engine to be more powerful than what's needed. Anything that's made is usually made, well, usually, not every component, but usually things are made to withstand more than what they're designed for. Example being hydraulic hoses or any sort of flexible pipe. Remember, we test a pipe to 1.5 times its working pressure. It might be designed to take 4,500 psi, but we only put on some hydraulic hoses 3,000 psi through them. We never put them to the full maximum work load. So same an engine, we'll design an engine to be able to provide a bit more power than required, but we tend to stop it at a certain point. And we design it as well So it's fitted to the aircraft that as long as the pilot is flying the aircraft in the correct attitude, speed, and with an envelope that's been designed for, the manufacturer in this case will guarantee, an example we've got here is what's called flat rating, is that up to 32 degrees Celsius and up to a thrust of about 100 or a fan speed of 95, he will get maximum thrust. Okay, guaranteed within that area there. All right. The roof, I call this the roof on the house, the flat rating roof as I call it. There's the ceiling. Yeah, that is, as long as the pilot flies within this range here, within this part here, the pilot will be guaranteed exactly the amount of thrust required. If they fly in a hotter environment, okay, they won't all guarantee the power available. There will be power there, but not guaranteed for this little section here, okay? And likewise, if he's got the engine going faster in a hotter environment, yes, there'll be thrust somewhere, but not guaranteed. So again, depends what environment they're flying in. As long as the pilot's flying within this ambient temperature and speed, etc. for N1 and N2, then yes, they will guarantee the pressure required in there, okay, and also the temperature as well. The roof on the flat ratings, I call it, that is the extra bit that's within the engine that potentially there's a little bit extra if required, but it also depends on the ambient temperature outside. So if they're flying higher, faster, or in a hotter temperature or a really cold temperature below this, the manufacturer will not guarantee that power is available. But so they must fly basically within this box, okay, of the settings of the engine, and will guarantee it. So this is what we call flat rating. The point of the ambient temperature scale at which power drops below 100%. So anything above that will be less than 100% power available. Okay. So aircraft manufacturer will probably use a process similar to the following when selecting the flat rating that best suits his needs. The user decides the takeoff power needed for the aircraft configuration, the route requirements, the runway lengths, the runway altitudes, the weight of the aircraft, and that sort of thing. So the pilot will input all information into the computer and work on how much power or how much thrust using his EPR and all that sort of thing to take off. In other words, can he take off from that runway? Is there a big mountain at the end of the runway that he needs to go up and over? Okay, hopefully not. The user calculates the highest ambient temperature at which required takeoff power can be obtained. So again, he might want to take off in the morning because it's cooler. If he leaves it too late in the afternoon, like in Nepal, where it's very cold in the morning but can get very hot in the afternoon, it might be too hot in the afternoon to take off for the size of aircraft and the cargo, the weight, the fuel, and that sort of thing. So that's what we call flat rating. Let's see, anything else in that one? No, that's pretty much it. There's an example in the book, gives you some examples of temperature differential and for altitude and stuff, again, on the flat rating point. And again, I'll just quickly go over that. I don't open the PowerPoint because you don't need to remember it as such. It says an example there, a flat rated as a specific thrust of 40,000 pounds of thrust, and that will be guaranteed up to a temperature of 30 degrees C. At temperatures above 30 degrees C, the 40,000 pounds of thrust will probably not be there. Okay, you'll still have power, but not maybe 40,000 pounds of thrust. At temperatures below the flat rating, thrust in excess of 40,000 will be obtainable. But using the graph like we saw there, on a flight computer, the pilot will advance the throttle, and for example, at 20 degrees Celsius, outside air temperature, you'll get 96% N2 and achieve 100%. Okay. Thrust 40,000 pounds is the example there. Now, in a note in the book, I don't have it on the PowerPoint there, the thrust reading available on the flight deck will not be in pounds or thrust. The pilot will judge the thrust being developed by the engines by actually looking at your EPR gauge. Okay, that will actually tell him how much thrust he's got. You will calculate how much thrust he needs. You will bug the gauge and be watching the EPR gauge. Now, your spools will be going as fast as required, but not necessarily providing the thrust because of the ambient temperatures. So this is why not just having an RPM gauge, but having a thrust gauge also lets the pilot know the thrust is available. All right. So by referring to the EPR gauge and by referring to N1 or a torque meter, you can refer to the section of engine thrust measurements for details. So it gives backup to the pilot. Like the olden days, they saw the RPM and just thought, well, the engine's going fast enough, I must have enough thrust. That doesn't mean the same thing. Analogy is, I use the running scenario. You go for a run in the morning and you're running a certain speed, yeah? You're running away. You've got enough energy. You run again another day, you run at the same speed, but it's a very, very hot day. You get tired far quicker, don't you? Well, an engine needs to be able to breathe properly. If it's not got enough oxygen for the same speed, it won't have enough power. On a hot day, you'll run out of energy very quickly. On a cold day, when you're running, you probably keep going a bit better. You've got more oxygen going in there. So although you're running the same speed, you don't have as much energy on a hot day as you would a nice cool day. And same for an aircraft. Depending on the load, the cargo, the passengers, the fuel, and the ambient temperatures will determine how much thrust that engine can produce as it takes off. In other words, on a hot day, the thrust might be there eventually once it gets the ram effect, so the aircraft must go faster. In other words, it might need a longer runway to get the eventual thrust it requires. And there has been instances where aircraft have not been able to take off and crashed because they've miscalculated the thrust required to the length of the runway or the environment they're flying in. Some airports are higher level, so higher altitude, less pressure. Well, that's less resistance, fair enough, but there's also less oxygen. So again, it's down to making sure you do your calculations properly. Okay, make sure the fuel figure is correct, the cargo, the weight, your baggage, all that sort of thing is correct. The temperature of the day, all input correct. And sometimes you'll do a manual check. They'll do a check against the graph as well as the computer just to back up. Because you never know, sometimes the computer can be wrong. Again, that's up to the engineers and the pilots to actually recognise that just in case that happens. Okay, so quite essential that it is done. But so quick recap, flight rating, as long as you're flying within the specified range of temperature designed for that engine, you will be guaranteed that set amount of thrust. If you fly out of it, then you're not guaranteed it. Okay. All right. There was another example down there as well. It just shows you same sort of thing, different temperature. So again, you can have a read over that. I think it's the same example in the old book as well. But it gives an example about 3,500 pounds of thrust at 59 degrees Fahrenheit. I'm sure we kept that one as well. So again, user decides takeoff power required. So it's up to the pilot at the end of the day to decide how much we actually do. Okay. Right, moving on to maintenance. All right, so once you're a qualified engineer, you can make your own helicopter, just like that one. Yeah. How safe do you think that one would be? It doesn't need much maintenance. I think the guy's got a good, I don't know what engine that is. What's that, a 125 or a 250? Okay. Fair play to him. You know, he's made it nice. It's actually working. I don't think it would take off very well. I wouldn't like to fly that one personally. But certainly as a toy or something to show them how it works, that's not too bad. But I think it might not pass airworthy standards, possibly. But certainly a good one. Okay, so maintenance, very, very important. Some maintenance we're going to carry out. So maintenance, the word maintenance means any one combination of overhaul, repair, inspection, replacement, modification, and so on and so on. So look at some terminologies. So overhaul. Restoration of an aircraft component by inspection and replacement in conformity with an approved standard to extend its operational life. It's not you just put in a garage and they'll try and fix it using their methods. It has to be an approved standard. Without a standard, we'll be all over the place. Repair, as it sounds, restoration of an aircraft or a component to serviceable condition, again, conformed with an approved standard. This is going to be the running theme. It has to be an approved standard. You can't go and just make it your own way. I'll try and fix it. I'll be okay. It has to be an approved standard. Inspection, examination of an aircraft or an aircraft component to establish the conformity, again with an approved specification. Again, you're following the manual of how to actually inspect it. Inspection includes mandatory inspection. This inspection classified as mandated by the Civil Aviation Authority. The inspection itself is actually for work. Scheduled maintenance inspection, which is an inspection of maintenance, including tests required again by an approved maintenance schedule. So it's just definitions of the terms we use. Replacement, as it sounds, any work operation which involves the removal and replacement of the same part or the substitution of an approved alternative part. So again, when you're doing your job cards, if you remove a component and replace it, make sure you say you fuel pump replaced in accordance with blah, blah, blah. If you put fuel pump refitted, that means you put exactly the same one back on. So be very careful when you're writing up a job card, you put the right terminologies in there. Because it means replacement, refitted means two different things. Modification, alteration of the aircraft or an aircraft component, again, conform to an approved standard. So when you are refitting, or not refitting, sorry, replacing a component, you make sure you check the modification standard on it, because you might get a part from stores that is the right part number, but it might not be the right modification state. It might be in stores for maybe 4 or 5 months, and within that time, they've maybe modified. I'll use a fuel pump example where they've changed a bearing or the actual drive shaft in the pump. They've made it stronger. So yes, the old pump will fit and work, but there's a chance they've maybe had a problem with the drive shaft that it tends to snap quite often. So they've modified it to be stronger. So there'll be a modification plate on the component, and the number, the last number on that plate is the last modification number. And in the manuals, which get updated, obviously, it will tell you to fit fuel pump part number 1234, modification ABC. Okay, or whatever the letters are. So you always check the modification matches the one that's on the part you're ready to fit, because the parts will look exactly the same. It's a modification state. Now, some parts can be brand new and alternative parts where the modification plate, there'll be no numbers on it at all, because it's a brand new replacement type. So there might not be a modification on it initially. Just check your paperwork, check the part numbers, and so on. A defect rectification. Defect rectification normally consists of an element of inspection and troubleshooting, followed by repair and replacement of the defective item. So you found something wrong, you inspected it, you found what's wrong with it, and you go and repair it. And repair or replace it, depending. So in dictionary, maintain is to cause maintain unaltered or remain unaltered or unimpaired. You're keeping it working without replacing it. You're just keeping it going. And this is what we strive to do with our equipment. We maintain. And all our maintenance is preventative maintenance. Yes, we do have reactive maintenance where something's broken, we go and fix it. But normally we'll try and prevent anything from breaking. So engines will only last in an airframe for so many hours, and they'll have to get taken out, even though it's still working. Keeping air in your tyres, keeping your fluids up, that's maintaining. You're maintaining the health of that aircraft and that component. Unfortunately, things will break, and that's just the way it goes. But where probably we do preventative maintenance. But you must consider the types of maintenance we are required to perform on our aircraft. So there's loads of different types. Inspections, well, yeah, if there's been an accident or something's gone wrong, especially here, so I've got an inspection team, they've trying to find, well, wait a minute, this shouldn't have happened. So why has our intake disappeared? Okay, what happened there? Okay, so someone's gone drastically wrong at this point. It's an investigation board, they'll come and inspect it, take some notes, photographs, and all that sort of thing. The gas turbine itself is simple construction, okay, and it tends to last a lot longer than compared to a piston engine. Some engines are now overhauled on condition only, so they're that good that they're only on condition only. But usually you've got things like turbines which have a life component. Good maintenance, keep an accurate record of all the engine operating parameters, thrust, vibration, oil, etc. And any wear and tear, degradation of the health of the engine, again, gets recorded. And that can help improve the engine through later years as well. But initially, before we go and get things sorted, we have a visual inspection. Always have a good look. So always check that nothing has been left in cowlings or intakes that could cause damage to the engine. Easily done. You might be working with tools, so every time you finish a job, when you sign for a job on a job card, you're also signing to say that you've done 100% tool check. The best thing to do is don't finish off the job card until all your tools are away. Now, you could be a big team, your supervisor will be in the job card, you'll be doing a task, you put your tools away, you come to the supervisor, yeah, job's done, he'll go, okay, sign here. And sometimes there's a separate stamp for stamping to say that 100% tool check has been carried out. But the principle behind any job card is once you've signed it, finished and completed, that is also saying, as I said before, you have actually done 100% tool check. All right? So never sign for any job until you're happy that you have put every single thing away from that job. Okay. And never sign for a job that you've never done as well. Always use covers and blanks, especially intakes and jet pipes. Yeah, if the aircraft sitting down for more than a few hours, put the blanks on, cover everything up. That keeps anything going in. Depends on climate. It could just be snow, ice, hot climates. Could be insects and birds and goodness what else. Doesn't take long for nature to find its way into our stuff. Always inspect the intake area, the intakes and the jet pipe prior to starting the engine. You just never know. There might be something down there that shouldn't be down there. Again, nature, it could be a bird. We had a jet once. We had a few jets that were outside all week, and one jet was just a spare jet. It wasn't getting used. It was just getting basic serviced. And one of the pods at the back, it's an electronic pod, only about that size at the back, about the size of your head. There's a hole in the back of it. And within a week, a bird had made a nest in it. Okay, so we couldn't take it out because of the laws here in Scotland. We had to get an official person to come here and remove the nest and put it somewhere safe. But it just showed you, in the space of a week, a nest had been built. This bird had seen this bit, went, oh, that'll do me, let's make a nest. So again, water ingestion as well. If you, depending on the type of aircraft, it's more for aircraft with long intakes, more for multi-aircraft. But certainly, water can damage a blade, and we call that what's called soft FOD damage, where if water is in a pool on the bottom of the intake, if once the engine starts, sucks the water very quickly, it will actually bend the blade, and we call it soft FOD damage. And that's recognisable by the tip of the blade bending forward, where the water's got behind it, gets spread out very quickly, and acts like a wall and actually bends the blade forward. And it doesn't take much water to do that. So if you do see water in intake, get a squeegee it out, make sure it's nice and dry. And likewise, snow and ice, always make sure there's nothing there. And any debris, it's a dusty environment, again, make sure you keep things clean. All right, intakes themselves. Any damage or blockage in the air intake would obviously affect the engine performance. So damage, loose rivets, just pure damage, the shape of it itself, that's going to cause a lot of problems. Make sure panels, fairings, security are flush. The usual thing people forget is to look around the side here. You can't always see in the top unless you're up here on top of the wing. You can see it in these parts to the side, you can see it in the inside here, but sometimes you forget to look underneath. Okay, so you'll see some people walk around and they put their hand on the side, a little bit underneath, but they don't get right underneath. Some engines are obviously easier to get underneath than others, but yeah, you should get right underneath. Make sure gentle tapping as well with your hand, and not let you hear if there's anything loose. Some quick release fasteners will look shut, but they're not actually shut, so make sure they are shut properly. Again, looking for damage around the intake. Again, it's a good one here. You can see divergent shape from the tip here to the compressor. Tiny little bit of convergent, but generally is a divergent shape. Again, just look around, look for water sit in the intake. All right. Again, as well as water, look for oil. If you find lots of oil at the front, well, that means the oil is dripping out the bearing. If it's dripping out the bearing, there's a good chance your labyrinth seal has worn. All right. And the debris that comes off the lab seal will probably be found in the chip in the oil system, so you can sort of relate to where it's coming from. You will always get maybe a little bit of oil at the front, not always, but sometimes you will. The more oil you find, the more wear that is. and it will only get worse. Okay, so again, that might need to be highlighted. So that's a good indication. And the same if you look in the exhaust. If you find any wetness in the exhaust or oil, again, that's not good. Any oil in exhaust, especially when it heats up, that could potentially go on fire, and we certainly don't want that. Okay. But as usual, checking for dents, damage, anything can affect airflow, any exits and entries like ducts and cowls. Again, any probes should be clean, free from debris. Electrical heated anti-icing marks located in or around air intake should also be inspected for adhesion. Make sure they're still sticking there. And again, it should be nice and smooth. You'll see right around this one, lots of rivets. As I say, just a gentle tap all the way around, and that will help you feel if there's any loose ones. Okay, very straightforward there. Okay. Compressor himself, well, you can only see so much of the compressor. You'll see the big fan at the front attached to the compressor. So yeah, the fan you can actually see. Again, all depends on the size of the engine. Compressor damage generally assessed as follows. So superficial damage, all right. So superficial damage and impact damage, repairable damage, all right. So superficial damage, form of small dents, may be acceptable provided it does not form they're all together. Now you get a lot of superficial damage on the back of a compressor blade, where the air is obviously hitting the front, but actually it sort of stagnates a bit behind it, and you get small indentations, which is normal. That's just standard on anyone. It's the ones you're looking for, the big indentations. Providing there's no evidence of too deep and too much, which can cause a crack. Any damage is potential to cause a crack. Yeah. The limits for dents and define again will be in the manufacturer's manual. Impact damage, as it sounds, anything that's hit it, caused by any small metal parts can result in damage. It can be metal, it can be soft, it can be water, it can be a bird, it could be lots of things. Anything that should be down there will go down there. If you see an impression of a thread or a hexagonal impression are visible on the stator or rotor blades, the engine should be removed for suit examination under normal circumstances. Well, you can almost yes and no that. We've seen that before. If it's a high bypass engine, yes, it might have sucked a bolt in there, hit the blade, and then gone out. But if it's gone down the compressor, that's probably going down the core engine. So what you would do anyway is, unless you're, if a big bolt's gone down, it's probably broken the engine. But boroscope it first, see if there's any damage. It might have, by chance, somehow gone down and out the turbine, not done any damage. If it's a small bolt, possibly. A large bolt, no. It will probably, if you go back to the exhaust, look at the exhaust, you'll probably find that your turbine's missing, or many parts of it. Again, so good chance will be rejection. So don't go and try and do a compressor blade blend, because you probably find, you look inside, the engine's broken. Repairable damage, again, damage caused by first stages, small stones, grit, again, that sort of stuff, that can be blended out, okay, in accordance with manufacturer's instructions. Later stages will have to be checked by boroscope, and if there's damage in there, depending, some engines allowed so much damage per so many blades per stage, okay, they'll get away with that, but it's down to manufacturer's limitations on that one. But if it's repairable, then great. Compressor casing, and that's compressor casing itself. Yeah, you're looking for things like leaks, damage again, components attached to the casings should be checked for security of attachment, corrosion. Some compressors are made of magnesium alloy, so that requires special treatments. Magnesium alloy, you can't just go and treat it normally, you have to do a specialist course for that one. But generally, common sense, if it's dirty, look for cracks, look like welds. I mean, it's usually a machined type surface, there's not usually any welds on it, but certainly some parts, any parts that are weak point, a joint, that's a weak point, so look for potential cracks. Remember, the casings is expanding, contracting with, if it's got ACC on it, for the rotor clearance, and that sort of thing as well. Okay. Combustion section, well, very hot, obviously. Same sort of casings. Combustion casing, you're going to struggle. Excuse me, you're going to struggle to see most external parts. It will be quite hard to see, but heat shields, lagging, refitted, signs of burning. Well, it's a combustion chamber, it's got to be burning on it, but hot spots. If you find a hot spot or a localized area of discoloration, it could be the combustion can inside has maybe got a crack in it and the gas is coming out, hitting towards one part. Again, any signs of leakage is not going to be good. We've got hot gas leaking out of there, and we certainly don't want fuel leaking out. Okay, so gas leakage usually shows as sort of black sooty streaks. Yeah. Heat shields lagging for security. It might be heat shields surrounded them, and where the fuel burners go into the casing, this should be checked for security, damage, etc. Ignition cables, routing, the little vibration. Again, check for burning potentially. Drain pipes, again, blocked for combustion chamber holes, potential fire hazard. And aircraft have drains collected tank. The tank may require to be manually drained. Okay, some will actually drain back in deflux, but some of them just need to be drained initially as well. Little tornado, we had to say before, we actually got a metal box about sort of this size, and we get control from the pilot to say, we'd say, go put the box, you go thumbs up. We'd actually walk behind the aircraft, put this box on the drains collector, drain, put a pin through it, walk back, give the thumbs up to the pilot, and he would cut the engine. And all the excess fuel, as the engine shut down, would go into this box. Very, very hot. You're looking at 70 degrees, you know, like a hot cup of tea. So you don't be touching that. So we'd leave it on there until we're done with servicing, let it cool down, take the box off, and then go and empty it in an improved container. Okay. So again, it all depends on, as I keep saying it, on the type of engine that you're working on. Okay. All right. I think what we'll do, I'll just finish off the turbine exhaust section and then we'll go for a break. So that'll be the next one now. So the turbine exhaust, again, you look at the front, you check the compressor, you look at the side of the engine, and then you come to the back of the engine and you see the big spinny thing at the back here. What's that big spinny thing going to be? This part here. All these rotor blades. Low pressure turbine, yeah. It's always going to be a low pressure turbine. I can just see in the cone, there's a little hole in there. Okay, so the exhaust cone, a little hole. What was that hole for again?
To maintain the pressure differential. Yeah.
Because you have a high pressure in here compared to the pressure coming out. So it equalizes the pressure, so it doesn't allow it to expand or contract as it's going up.
And now, some cone has also a hole beneath that cone.
Yeah, it will do, yeah. Access as well.
Yeah, right there, yes.
Yeah. You have obviously the hole.
Yeah, sometimes it has a leakage of some lubricant.
It can do, yeah, because that's the bottom of the engine. Now behind that is your turbine disc, your rear bearing, and if the seal is leaking, oil can go into the cone, and you're quite right, that'll go to show an indication of oil. Now when the engine's running, it'll probably burn away, but that will be shown as a black streak. And you can almost see on this photograph, there's little streaks.
Yeah.
Carbon, just little streaks. Again, if it's a bad leak, it'll be a very black sort of tarry streak.
Black, yeah.
And just by looking at the colour of the turbine blades, now obviously turbine blades are getting very hot, but you will recognise colours, normal colours as they go. If they start getting really, really white, that's a good sign it's over temping the engine. Again, really, really black, that's a good sign there's maybe a leakage somewhere. And likewise, in the diffuser part here, or this type of engine doesn't have a long exhaust, it's just a very short system, but any discoloration in here or on the support struts here as well will give you an indication what's maybe going wrong. Could be metallic debris. And the ones we look at are these ones. If you get any aluminium bits of metal out, you'll get what's a dull white or a silver type splatter, like a sparkly effect, yeah? That's indications possibly aluminium. Now that could be from hitting the casing internally, so something's been wearing down, which shouldn't be, quite shiny. If you get titanium deposits, that's usually bright blue or sort of golden speckles. That's titanium, so the turbine could be touching the titanium shroud, okay? And that can be causing problems. So again, that would have to be investigated, that would have to be boroscoped to have a look at. So any streaks, which normally at the end, they do get a dirty engine, but it tends to be, if it's working correctly, it should be dry and relatively all the same colour all the way around, thereabouts. If you start seeing localised areas of colour, that's not a good sign. That's maybe, you know, we're not quite getting there. And any bits of debris, either white or silver, is aluminium, blue or golden is usually titanium. Now, the blades themselves, you don't tend to find much damage bar from normal erosion. It's very, very small pitting, but the only thing that's going to happen is cracking, and usually on the tips of the blades. I've gone down, I've seen a whole turbine section just missing. We've seen the roots of the blades left, and that was it. Or we've maybe seen one blade has snapped off and gone out. Looks like you've lost a tooth. All right. So again, just watch out for that. So take your time. And this engine, yeah, you can get in there, you can spin the engine. Now, if it's an LP turbine, we can go to the front, get somebody at the front to spin the fan, and that will spin the LP turbine for you. And if it's a dark environment, use a torch, nice and slow, you can have a look at it. Yeah. And take your time. Look at different angles. Look from one side angle, you'll see behind the leading edge, and then the other angle, you'll see behind the trailing edge. Yeah, just take your time. And just keep it consistent. If it's a big engine, up to you how you start it. As long as you do it the same way, it doesn't matter. Look at the front, look at the tips first, spin it, and then get to spin it again, and maybe look at the roots, and then work your way back and forward. And take your time. Don't spin it too fast for safety, but certainly take your time. The same way you're checking the compressor. Do it in a methodical, logical process. Don't just have a quick look around. I've seen some guys go to an engine and they go, yeah, that's okay. That's taking 2 seconds. It's so easy to miss something. And we teach our students, we take some blades. I'll give them 3 blades. One's got no damage, one's got a little bit of damage, one's got a lot of damage. And I'll tell me which one's got the most damage on it. And oh, they're okay. There's one blade has a good bit of extra bend on the tip. Very easily missed, but that's why take your time. It's so easy to miss something. And it's usually a bit embarrassing when another engineer's going out after you and they say, oh, did you find that damage on the blade? No. So again, don't let another engineer find what you should have found to start with. Okay. And don't be frightened to, if you find damage and that aircraft's got to fly, don't go, oh, better ignore that, it's got to fly. Well, at the end of the day, you've got people's lives in your hand. If that's not right, that could go wrong. Highlight it. There's always another jet available somewhere. Yeah. Yes, it's a bit of awkwardness, and you know, it's not ideal because you want to get a jet off the ground. But you should never be pressurising to sign for anything. Never press to get an engine working when it shouldn't be working, or an aircraft flying when it shouldn't be flying. Okay, so always put it up through your supervisor levels. All right, so yeah, light deposits there may be assessed in terms of damage performance. Heavy deposits might need removal. If you see big heavy deposits, which is not the normal, then yes, they should be removed. Okay. Jet pipes, turboprop engines are not so highly stressed as turbojet ones because the propeller's doing the work. In a turbojet like that, then yes, all the gas is coming very, very fast. So turbojet pipe attachment joints, etc., for cracking, expansion, check the airframe, anything connects to. Again, make sure checking the discoloration, blistering, and any sort of curing. Anything's attached, make sure it's secure, and it looks okay. Again, you'll learn through experience what looks correct, and then so that day you go out and go, hey a minute, that doesn't look right. Again, it also depends on the colour, sorry, the light you've got available with you. We did a service on one jet down south. The pilot was doing his walk around, and he looked at the back of the exhaust, and just by chance the sun was right behind us, so the sun was really bright and really looking into the exhaust. You can actually see a lot more than normal, and it's always quite a dirty environment where the thrust reverse is. And the pilot goes, I think there's something wrong. So I'm looking, I'm going, no. He says there's something different. I says, so the only thing that's different is we can see it more clearly because the sun's behind you. He says, I've never seen it that clean before. So he thought there was something wrong, only because it was better light shining on it. Okay, so again, make sure you've got decent light to see what you're looking at. Okay, right, we'll stop there. Let's go for another break. That's a bit later than planned, but that's fine by me. I don't mind. What time on now? So I just have to call back. So yeah, come back in about 20 minutes again, guys, and then we'll continue with another bit. Again, refilled and completely with the new oil. Now, most of your oil systems are recirculatory. You will lose a little bit of oil, but most are self-contained. One of the jets I worked on was what was called a partial loss. It wasn't a total loss system, it was also called a partial loss system, where after maybe an hour and a half of flight, it would use almost a litre of oil per hour, okay, depending on the flying conditions it was doing. So although it was a recirculatory oil system, it was still, by the nature of the type of system, would actually go through quite a lot of oil. So it wasn't a total loss system, it was classed as what was a partial loss. So we didn't have to change oil, we just kept topping up, so it was cleaning itself as it was going through, but certainly some more of the commercial engines, they tend to keep it in. You will have to top up every so often because you will lose small droplets of oil through the breather and that sort of thing as well. Yeah, good old magnetic chips in there. Okay, they help keep us for diagnostic problems. Always a good thing. Should be removed and examined at regular intervals. Not just you decide. They will be scheduled in for every so many flying hours. Again, I keep using jet. I used to work on an example. Engine chips were removed every 32 hours, and SBS chips were removed every 60 hours. Okay. For commercial aircraft, it might be 100 hours because they're not under as much strain as military ones. And if we do find debris on it, we find there's a trend going on, and what we'll do is we will be suggested that we inspect the magnet chips maybe half the time scale. So sometimes if we found debris on chips, we'd reduce the flying hours down to 16 hours. Every 16 hours, we would check the chips again. Now, military aircraft, a jet would only fly for maybe 1.5 hours at a time. So every 16 hours, that's maybe, you know, it could be about 8, 9 flights. Commercial aircraft, if we were doing it every 16 hours, you'd be doing it every flight, because a flight to America and back, well, there you go, there's 2 flights. So you tend to find commercial ones tend to be a lot longer between each flights. Unless, of course, they do find debris and you have to reduce it. Some modern detectors require use of a 250 volt mega to check the resistance across them. Okay. 0 ohm resistance would indicate there are sufficient particles on them and want removing the detector for examination. So that can be part of the DMS system, debris monitoring system, that one. Mountings, very crucial. Okay, you can see there's been a bit of damage to this one. A little bit of damage. Well, there's part of the engine that's disengaged from the actual engine. All right, so obviously the engine's broken away. Maybe the fuse is gone, and part of the engine has actually been left with a mount. So thankfully, the engine mount, all this part here, has done its job. See the big bolts going into the engine there, and there's the linkages, which will contain spherical bearings. But if you actually see here, this is actually part of the engine that has been left. So for whatever reason, you can see the engine, another pylon's still there. So whatever reason has happened, this whole engine has fallen off. It's broken away from the casing of itself, not the mount, the actual casing. So yeah, that'll be in somebody's field somewhere. So yeah, examining mounting should be examined for security, cracks, etc. And the cracks, you are allowed so many cracks in a certain area and a certain amount. And there are ways of dealing with cracks. More for fuselage, we can stop drill them to stop the cracks going further. Some cracks, we can't get about it until the engine comes back out. But certainly the mountings, we find any cracks in the mountings anywhere, then yeah, that's a big no-no. That needs sorted out. Corrosion, we can remove and reprotect, repaint in accordance with manufacturing instruction. Dents, as we spoke about the other day, bowing, remember the 1 in 600 rule. Dimension, checks the dimension, discoloration, fatigue. Again, shock loadings as well. If you've had a shock loading, which potentially could be in this engine, you might have to take the engine out anyway. You know, the fuses might have been stretched. Check torque loading and bolts and tension. The loading will indicate the bolt has stretched and should be renewed. Well, if you find yourself tightening the bolt up and it's stretched, there's a good chance it's going to snap because it's going to put more stress on it, unless it was genuinely slack. So certainly the ones we had on, we would initially tighten them up, do a ground run, and then retorque it once it cooled down to a certain amount, and that would be it. Some of the cooling pipes are the same. The cooling pipes attached to the engine. There was a V-band clamp, a hot air pipe that if the hot air escaped, it would actually burn through the fuselage. So again, we'd check it, and it was allowed so many turns and so many checks. If it exceeded that, we'd have to replace it. So there's a lot of checks to be done when fitting an engine. Okay. Tuttles, yeah. Crack check should be a magnetic flaw type. Okay, so a lot of NDT, non-destructive testing, if you suspect a crack. So it's external, internal, good old endoscopes or borescopes as we call them. Basically, you put a flexible or rigid type pipe in there, it's got a lens on it, and we look down the lens and we can check far more detail inside and potentially stop some more damage happening, or keep an eye on cracks that might be already there that we can't physically get to from outside. Right. So the probe itself is an optical instrument which performs two functions. First one, it will display a sharp, undistorted image at the eyepiece. Now, it could just be a manual one if you look at an eyepiece, or you might have the fancy ones like this. I say this is fancy, this is actually an older Video 2000 model, which you've got some in the hangar, which uses the students have a little monitor there, and actually plug into a bigger monitor. The bigger fancy one these days, they can actually measure in 3D. So you can actually download information and email it. Back in our day, this is one of the newer ones, which is out of fashion now, but it still gets used. It's got a flexible tip on the end, so you can move the tip about to find out what you're looking at. But take a still photograph and you send that away for expert analysis if you couldn't decide what it was. I said in the olden days, we'd have to put in what's called a flash card, like a big disc, go and post that to the company, and that would take maybe a week or 2 weeks to come back, so there'd be a lot of delays. But obviously nowadays, everything's in an email. You can take a shot, upload it to the computer, and send it via email. We can get information back very, very quickly. Right, so there's lots of different types you will come across. Again, just get trained on them. Okay. So yeah, first time, display a sharp, undistorted image at the eyepiece or on a screen, and to direct a beam of light for illumination. We have a light source going down. Without a light, you can't see inside. So you need decent light. Always hand this equipment very carefully. It's very easily broken and very easily trapped. And especially when you're turning compressors and turbines, if you put the probe too far in, there's a chance you can catch it on the blade, get stuck, and it comes off, and you can't get out, and then you have to take the engine out. So you've just ruined a lot of work. Okay, it's not very clever. If the probe is a non-adjustable type, the angle of view will come as a fixed set, and you can change the angle of view, obviously straight in, backwards, forwards at an angle. And we've got a few different versions here, and there are 4 variations. The straight view, where the center of field is parallel to the probe shaft itself. So as you're looking down, you get the straight view, it is as you're looking at it. Lateral view, where the center field is at right angles. So basically, you've got the probe going that way, but the view is going that way, which is good for turning around and looking that way. So you can't get the fixed probe to turn, but you can actually turn the lens. Okay. Oblique view, where the center field is at an oblique angle, about 45 degrees, usually, thereabouts. View, which is basically a double back on itself. So if you're looking down there, you're actually looking back towards you 180 degrees. So a very, very acute angle. So that's an amount of a double back check. So that's if you're using a rigid probe. For the likes of these ones, the twistable nozzle, you've got a little joystick on the controller, so you can actually move the probe round about, in and out, and back to front, and that sort of thing. And you can actually lock it in position. And even the fancy ones, now some of these equipment cost up to £20,000. This was an old XL 2000 back about 20 years ago. But still, we still use these in the hangar at the moment. It's still good for training purposes. And you probably find something like that as well. They have a fireproof fire source, power source, usually a battery pack, all contains in a big box, so everything is there as you require it. And again, there's a connection there, you can actually connect up to a big TV monitor. So you can have one person looking down, sorting out, and you can look on the big screen. Similar idea that you see in hospitals. Hospitals use a very similar sort of scope as well for checking inside the body and all that sort of stuff. They're very similar. It can get a bit disorientated when you look in the engine. Somebody would turn the gearbox to turn the HP, and there'll be another part for the IP shaft as well. LP shaft, you just spin by hand. But certainly you need to know what you're looking at. The further into the core of the engine, once you're getting closer, so you might have to do what we call map a turbine and NGV. So you might, if you know where you are, you get your angle set up. If you're at the top, you're at the 12 o'clock position. As you go further in, then you go into the 1 o'clock, the 2 o'clock, the 3 o'clock to a certain point. Then you come back away, it's 11 o'clock. So it does get a bit disorientating as you look in. So when you're mapping any faults, if you find any fault in a turbine blade, put a brief description down. Is it the leading edge? Is it the trailing edge? Is it the first stage, the second stage, and so on? If it's NGVs, is it 12 o'clock, 6 o'clock, 3 o'clock, 9 o'clock, that sort of area? and is it the back of the blade and that sort of thing. So as I say, it takes a bit of time getting used to what you're looking at. It's fine looking at something, you find a problem, but you have to be able to interpret what you're looking at to actually describe. And obviously when you're looking inside a 10 little probe, it looks far bigger than what it is. So what you think might be a crack might be like 0.1 of a millimeter. That's where the new equipment, like not this one, but the newer version of these can actually measure in real time the size of the crack for you using a 3D lens. Very, very clever bit of equipment. And that's the iPlex kit, as we call them. They're the sort of more favourable ones for measurements. Whereas before, it was down to the engineer's eye, and we'd use a blade as a reference. So if we found a problem on a turbine blade, we'd have a spare blade outside, and we could sort of guesstimate the length of the damage or wherever the crack was as well, just by comparing it to a natural blade. So preparation, first thing to consider is what equipment you're going to use. Are you going to use a manual probe, a rigid probe, or one like it's got here, a flexible probe? All right. An engineer using an endoscope will have all the sensors concentrating that image at the eyepiece and be unaware of the events around the work. So yeah, you're concentrating on the engine, but you're forgetting what's around about. If it's a busy environment, again, be very careful with that. Safety personnel should be accompanied in the case of a fire, flood, or anything else that could affect you, because you're concentrating. There's usually two people doing this anyway, depending on the equipment you've got. I mean, you can go out and do it yourself, but something that's handy, the person maybe using the control or the rigid one, you know, you're looking then if it's a manual one, somebody moving the stuff for you as well, as you see fit. Again, sometimes you might find something you're not sure, different people's vision, although you can refocus the lens, it's worth getting a second opinion. You think, I'm not sure if that's a crack or is that a bit of dirt, get somebody else to come in. And again, maybe get another person, get 3 opinions before, because if you make a decision, oh, that's a definite crack, and you take the engine out and it's not a crack, you've just wasted a lot of time. And again, I've had that before. I was called out to an engine with a suspect crack. My colleague who used to work with, he'd sent his other person to check it, and it was him that said it was a crack. My colleague was an ex-engine bay person like myself. I went out and I looked at it, a bit different in my eyes. It was just a streak of carbon. It was just a dirt. It wasn't actually a crack. So luckily, we didn't take the engine out. But again, just second set of eyes. Take your time. If you're not sure because you're looking into it, unless you're looking at the monitor like that one there, it can be a bit disorientating. Okay, so just take your time. But don't be frightened to ask, could somebody else have a look? I think it's a crack, or is it a crack, or is it okay, is it acceptable, and that. Sometimes it can be a bit awkward to figure out. Other factors, before you go and open all that up, you've got blanks around the engine for the inspection blanks. So let the engine cool down. Okay, dissipation of heat. Watch out for windmill. If you're outside, the engine could be spinning over. So before you put anything down, make sure you probably better put the blank on to stop the engine spinning. Endoscope equipment contamination. Don't get any fuel, oils, electrical potential difference between light source, aircraft structure, fuel, and all of this. Now, saying that, they're all battery pack operated. They do get mains ones that must be used with a flame-proof power source as well. Okay. So if they're non-rotating assembly, things that are fixed, you can access ports are used. All right, direction of view, how to report it, which way you're looking in. I was looking forward, I was looking rearward, I was looking straight in. So when you write a report about something you find, the area, component inspected by name, for yourself and or number, the date, time, aircraft, engine, position, that sort of thing. Dimensions, any type of damage you find. Again, if unsure, as I said before, get somebody else to maybe confirm it for you. Rotating assemblies, again, same sort of thing. Compressor access ports used. You get compressor access, it could be turbine access. Directions of view again, details of damage. The turbine access ports used, the turbine blade number visible from the center of view. Well, the blade number might be a hard one because they're not usually, you won't see numbers on them, but you can say if you find a mark on the disc or somewhere, you can use a reference. You might call it the 7th blade from the center of the disc that has the little, you might see the serial number, something can identify, or you might just say times 3 blades found to have damage on LP turbine or HP turbine, IP turbine, on leading edge or trailing edge or mid-level blade, that sort of thing. As much information you can provide. And then normally with these borescopes, you can take a picture, upload it to the computer, and send it to the manufacturer for confirmation. If it's not quite within limits or it's just outside limits, they might give you a concession to say, okay, we'll give you 10% extra lifespan on that because the engine's due to come out very shortly. Or they'll say, no, it's fine, yeah, it's definitely out of limits. So if you're unsure, get a second opinion, get in touch with a representative, and they'll come and double check it before they actually take the engine out, if it's that bad. So sometimes as well, when you're spinning the rotating assemblies, it's important to know the number of blades in a particular stage. So you can be spinning around. You need to know, have I gone around enough blades? As you've got the person rotating the gearbox, you'll be counting the blades nice and slow. And let's say there's 30 blades on a disc. You'll find one blade that's maybe got a specific mark on it, maybe a bit of dirt. Use that as a reference, and then get your call to spin it. And then once you've counted the blades, and you're happy you've checked all blades, that's fine. Then rotate your borescope to get maybe the leading edge or the trailing edge. Go in, go out, and do that as many times as you see fit to. It's very easily, if you go too fast, there's a good chance you might miss a bit of damage, even by blinking. As you blink, you might miss the blade. So nice, steady, slow. And it's up to you to tell your colleague to hand on the engine the speed you're happy with. All right. So yeah, make sure you know how many blades per section. And the whole stage has been checked. And then checking larger blades, several passes may have to be, again, to check the whole blade from front to back, left to right, and so on. So I said before, LP shafts can turn by hand. IP shafts without a gearbox may require a special tool, which is a blank, usually behind the LP compressor, and that goes in to spin a certain tool. But also the HP one, that gets used by a turning access point on the gearbox, because the gearbox is attached to your HP spool. So again, anything you put inside to look at the engine, be very careful how far you put in. Just put enough, get it to rotate it slowly, then you can go further in. Always tell the person to stop, always do it slowly and as much as you can see. Okay. The damage you might come across. Okay, so impressive foreign object damage. What I was going to say before, actually, with the blanks themselves, the actual blanks you get access to go in borescope or put an endoprobe in, is the blanks must be put back on with suitable lubricant. It might be engine oil, it might be a special anti-seize compound, and must be torque tightened. Don't just put them on and put your own effort on there. They must be torque tightened. Don't put it on hot, let them cool down, because you can cross thread. If you cross thread the blank area, that's an engine removal. There's very hard, apart from certain occasions, you can actually sort the thread out by a helical insert because you probably put foreign object damage in there. So be very careful with the blanks. Make sure you don't put them back on dry. Make sure there's a standard lubricant in there and torque wrench as well. Now, some of the blanks have little probes at the end of them and they're with different lengths. So make sure you put the right blank in the right hole. Too long one and a short one, it won't fit. But likewise, a short one can fit in a long one because the hole's excessive. So there's potential we could fit the wrong one. You might have seen people try and fit the long one and a short one. They put a bit of pressure on it, they've turned it, they've actually bent the probe at the end, which obviously doesn't seal properly, and that lets hot gas come out. Because the blank doesn't blank the casing, it also blanks, especially for turbines, the turbine casing inside. And if you don't put it in properly, that blank will not seal off the access hole for the turbine. Well, where's the turbine gas going to go? Straight back out into your LP cooling duct, and that'll probably give you a hot warning light in your cockpit. So again, take them out one at a time. Some people take them all at one go, just for preparation, but it's probably easier just to take one at a time, check it, put it right back in, do the next one. That way you can't go wrong. Most of them are self-explanatory where they go, so you usually can't go wrong, but some are very, very similar to each other's. Never force one in. Okay, FOD. Yeah, we've got foreign object damage. Stuff we don't like at all. Okay, let's see where we are. Anything else to think of? That one's. That's fine. Okay. Find your bore. Oh yeah, I probably mentioned before going to FOD. Let's just double check some minute. Just double checking and manage that one. No, that's okay. Just make sure I'm finishing it there. Okay. So FOD, any ingestion of FOD, I said before, if you see a slight bit of damage on the front of the compressor blade, there's a good chance there's more damage through the engine. So first things first, I will look at the turbine, see if there's any damage on the turbine, any speckles of aluminium deposits or whatever. If not, fine, well, then it's time to bore scope, have a look inside the engine. So compressors, again, do a systematic survey, a compressor, fight for crunches like a bird. If a bird's hit it, it's obvious, it's going to be a big stain, you can't miss it, and it smells like a smelly thing. Good external examination first, and then progress to your internal bore scope inspection. In addition, the probe ports provided, it may be possible to use bleed valve apertures. Anywhere you might need to get access, sometimes hot air offtakes might be in an awkward bit. If you've got a low bypass engine, like one of those spares used to take the air offtake off and actually look inside the bleed valve and get a good view backwards and forwards. And we tend to use that for a bit of training purposes, again, back here at the hangar. FOD damage, the main common reason for inspecting compressor. Centrifugal compressor resistant to FOD damage is because it's maybe a very robust one, but not immune. And actual form compressors, fairly fragile. They are strong, but because they're spinning very fast, anything that hits them can cause a lot of damage. So things like that, nicks and dents, blades coming off, you can see there. Not normally, it's good to leave permanent marker on blades. That's probably a bad practice there, because that can cause corrosion within the material. So whoever's done that, that's probably not a no-no. Shouldn't really do that. That X there, that's a common practice of marking the top blade. Okay, maybe at a reference point. If you're checking fan blades, check at the bottom, especially in the big engine, your big engine on 747s or whatever like that, your big huge compressor, we'll bring the blade down to the bottom, start at the bottom and just move the compressor blade one at a time from the bottom, look up and down. That saves you looking at the top as well. As you see there, if you find a tear in the blade, big no-no. No, any tear, that's an instant rejection. So you wouldn't even bother going to try and fix anything else. Okay. Obviously a chunk missing, that's definitely an engine change. You can see there's a nice round shape there. Now that could have been the point of impact. That might have been a bolt or something's hit it. And as it's hit it, it's caused damage, which caused damage to that blade to eventually knocking this one off. But if you look further back, you just see in this blade here on the the third stage rotor, there's a bit of damage on that third stage rotor as well. So if you find anything in the front, there's a good chance you're going to find damage towards the back. Something's obviously hit this one. Now this one's weird because that part there is actually a blend. It's actually this blade has been blended, but unfortunately something's hit it later on and bent it. So we can see a little bit there, bang, and bent it there as well. I mentioned soft FOD damage with water. Water can bend a blade like this. It won't do that, it won't make it tear, but can certainly bend the tip of a blade forward. Okay, so if you watch out for that as well. Some of it might not be very noticeable, some of them very, very small. You might only get something like that, a little tiny mark on the blade. And you think, that's okay, there's nothing. Well, that might have been something that's gone through the bypass, gone through the compressor, into the next compressor, and gone through into your turbine. So although they might see a little bit there, double check the turbine. If in doubt, bore scope it and find out if there's any more damage. All right. Anything else on that? Interference between tips and shrouds casing can cause damage caused by surge. Again, a surge can cause a blade to come forward, and indeed you might get shingling, where the snubbers might go over the top of another snubber. Okay, so like this one here might go over the top of that. Very rare, but it does happen. Look for bending, cracks, etc., and so on. Again, all the information laid down for each specific blade, but definitely in your blade areas, you're only allowed to fix certain parts or blade certain parts. The casings themselves, okay, yeah, you've got the top casing, bottom casings, wherever. Know how many rotors you've got, you might have to inspect further in. Damage on the casings, again, it all depends, and depends on the type of environment you're in. If you're in a very sandy, sort of dusty environment, now Nepal can be very dusty and sandy, as you well know. So in an airport environment, that sand getting drawn into the engine can act as an abrasive and start wearing things out, blocking cooling points off and all that sort of thing. Okay. Oil deposit blades, the indication is front bearing wearing. Again, so you're looking not just for damage, but I've mentioned already, oil indication and other bits. And say dust conditions can also, you might have to do a compressor washing because it will embed in there. All right. So example of the blades. All right, so there's some snub oil. You can just see some tiny little indentations there, some little scuffs here and there, and if you probably just make out, there's a little crease just around this part here. Yeah, just a little crease. Now that looks like a shadow. It's actually a little crease on the blade. So again, I can just see a tiny little dip on the top of the blade there, and very closely, you might never see this on your computers or your what have you got at the moment. There's a tiny little nick just on the edge, the leading edge of that blade there. So again, some of the damage, not exactly obvious straight away. Take your time, and if you can feel it, put your hand up the leading edge very carefully. Don't do too fast because if there's any jagged bits, bits are sticking out, they'll cut you. So just nice and gently, using your hand as well as your eyes is a good indication that you might find some damage. Okay, but take your time. So look up the leading edge, look down the front face, and then get behind it as well. You won't get right behind it. Can certainly change the angle of the torch if you've got the compressor, the less compressor. The bigger the blades, the easier to see. But use your hands as a feel gauge, and that'll help you out as well. All right, let's see what else in that one. Just want to see on the compressors, want to check on there as well. Done that one. Yeah. It's fine. Okay, let's go on to combustion and then we'll go for another break. Right, combustion chambers. Well, you can only inspect these with a borescope equipment. You can't see it externally, obviously. Depending on the type of engine, normally the type of engine you'll have will be a what type combustion chamber, which this one is. Can anybody identify this one?
Angular.
Yeah, standard angular, which is most common you'll come across. And there's lots and lots of cooling holes, there's lots and lots of joints for the burners, igniter plugs, etc. Okay, so any hole, anything which is a weld is a weak point. Now, obviously, the combustion can is contracting, expanding with the heat all the time. So, usually as a result of excessively high temperatures, you get discoloration, burning, cracking, distortion, erosion, and etc. Same for the NGVs after there. What you have to watch out for is what's called unzipping. Okay, it's not in the book, just a good thing to remember. Where there's lots of, probably inside the liners here, you've got the outside liner and internal liner, is where there's welds or lots of little cooling holes. If one cracks, that's a stress point, and then it'll crack to the next hole, and it'll start to literally unzip all the holes to the point you can also get the combustion can split in half. We've had occasions where an older version of this, the can pretty much split all the way around because it was made of two different materials. Well, that wasn't very, if you think about it now, two different materials welded together in a hot environment, probably not the best design feature. So nowadays, the angular ones are made from one material, usually one material or a coating at least. So that prevents differential expansion. NGVs, you might have some sort of guide vanes as well. So there'd be cooling guide vanes because obviously the burner will be going back that way. This would be the front of the combustion can. This would be the rear of the combustion can. So you might have some guide vanes as well, or outlet guide vanes as we call them. So the bypass air going through. But again, take your time, go round inside, go inside the igniter port if need be. Again, the burners will be in as well. Do you remember what type of burners were fitted to a combustion can? Anybody remember? For an angular type one, what type of burner would you fit to an angular type combustion can? Would it be an atomizer or a vaporizer?
Atomizer.
Vaporizer B.
Vaporizer, well done. Yeah, vaporizer. Yeah, angular cans tend to have vaporizers in them. The multi-can, the multi-chamber ones, can angular ones, they tend to have atomizers. Vaporizers, which are also known as, what are they also known as? seems like weeks ago. That was last week. What's a vaporizer also known as because of the shape? Most burners look the same shape. The next burner I show you looks like one anyway, but a vaporizer also known as a hockey stick. Hockey stick?
Hockey, yes.
Yeah.
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 Hockey
Just
is in opposite
remember-
direction.
Yeah. The vaporizer would be facing back towards the front of the engine here, but an atomizer will be facing in line to the rear of the engine. Okay, so usually vaporizer for these type. Any other cans usually an atomizer normally. Okay. Right, how are we doing that? And then, yeah, that'll take us to the burners. How are we doing for time? Right, okay, let's go for another quick break. Another 20 minutes. We'll do burners and then let's see where we are. I'll go through some other bits and pieces in your book for there. Finish on the burners and then we'll do. I'll leave it. Yeah, we'll leave it there. We'll finish on burners after tea break. A little bit of recap, and that'll again do for today. I think. Just check where I am. Yeah, we'll do repair tomorrow. Finish off repair. Oh no, well actually no. I'll tell you what. Yeah, go for a break. We'll finish off inspections and repair. A little bit of recap. All right. See you in about 20 minutes again, guys. Okay.
phone and start dialing. I want you to deal with your problems by becoming rich. All you have to do today is pick up that phone and speak the words that I have taught you. And I will make you richer than the most powerful CEO in the United States of fucking America. I want you to go out there and I want you to ram Steve Madden's stock down your clients' throats till they fucking choke on it. Now let's knock this motherfucker out of the park!
At 1 p.m., we opened the stock for sale at $4.50 a share. By 1:03, it was over $18. Even the big Wall Street firms were buying.
Hello. सबजना छ हो नबोलेको मात्रै हो
जम्मा 11 जना देख्छु त 15-16 जना छ भन्ने सुनेको थिएँ त हैन
16 जना हो 16 जना यहाँ पनि नहोला
सन्तोष बस्यालै छैन त ए भारती खोइ त आज नि रुम सर्दै छ क्या
मोडुल 17 देखि उ रुमै सारिरहेछ
त्यही भने 2 हप्ता हुनलाई छ यार रुम सारे पनि
दुईटा मोडुल भइसक्यो उ रुम सारिरहेछ
त्यही भने
अझै ऊ 11 मा पनि सारिएर बस्छ, रुमै सारेर बस्छ।
हाम्रो दिगु कमरेड कहाँ हराएछ? बोल्दैन त। गाना साना पनि यसो बीचमा बजाउँथ्यो, त्यो पनि छैन।
अलिअलि रिफ्रेसमेन्ट पनि हुन्थ्यो नि केटो।
त्यही भने
पपुलर कुरा भयो त केटाहरूसँग।
ए खगेन्द्रलाई भने मैले, सरोज मैनालीलाई पनि भने, अरू कसलाई भन्नु पर्यो र?
अरू त कसैले छैन, त्यति नै होला नि। अब हामी अघि 5 जना भेटिहालेको थियौँ के अरे, अब अरू 5 जना
कृष्णलाई
मैले भनिसकेँ।
पहिला रुम सारिसकोस् न अनि भनौँला। खोइ त देखिन त। ए आइएम सन्तोष बस्याल लेखा रहेछ नि त।
भर्खर आएको के अरे, यो नयाँ बुक आएको हो र केटाहरू?
आइसक्यो त, पाएनौ?
लौ हो र भने
छैन पाएको।
अनि छुट दिँदैन जस्तो लाग्यो मलाई। यिनीहरूले के खर्च गर्थ्यो त?
ए सोन, साँच्चै म तिमीलाई अघि पनि भन्न बिर्सेँ यार, तिमीले बुक किन नमागेको त्योसँग?
छैन रे त।
तुरन्तै प्रिन्ट गरिदिन्थ्यो के तिमीले अघि कर गर्न, मैले त्यहाँ अगाडि भन न, बाहिर आएर भनौँला भनेर सोचिरहेको थिएँ होइन। ए के त्योसँग भएको प्रिन्ट गरिदिइहाल्थ्यो यार, त्यो दिगम्बरकै खान्छले।
अघि नि यो कति यो पेजहरू स्किप भएछ लाग्यो। अघि 99 पेज छ नि, 99 त्यही त 99 100 101हरू छैन कि, पढाएन नि त। मैले हेरेको थिएँ डाइरेक्ट स्किप भयो है, कहाँबाट पढाएछ भनेको यस्तोहरूको त। त्यही त
अनि प्राय स्किप गरेर पढाइरहेको छ क्या अहिले।
त्यही त
त्यति हो, रिभिजन गर्दाखेरि भेटे नत्र छैन, त्यही हो। के
अहिले अनि के गर्नु नि?
अब रिभिजन गरौँला नि।
त्यही त अलिकति टिप्स पनि दिएन कि यसले त। भन्नाले जुन हुन्छ यसो रेड अलिकति अब कुनै इम्पोर्टेन्टै हो कि भन्ने टाइपले।
होइन पहिला त दिएको थियो, अहिले चाहिँ नदिएको हो।
अब रिभिजन दिएला नि।
रिभिजनमा जुन
दिगम्बरले बोल्दै बोलेन यार आज।
सुतिसकेको छ कि केटो? दिगम्बर अनलाइन रहेछ त्यो त, अनलाइन त
के छ?
आज खोइ त
परमेश्वरजीको दर्शन पाएन भन्नु पर्यो खोइ।
परमेश्वरजी त अघि नै यही हुन्छ तु सुनिराख्नु भा।
जेमसले नि माइक अन गरे है अब चाहिँ।
नयाँ बुक केटाहरूले त्यो कन्टेन्ट कसरी दिएको छ? यो पुरानो बुक जस्तै छ कि नयाँमा छुट्टै कन्टेन्ट दिएको छ?
कन्टेन्ट भन्नाले कस्तो बे?
कन्टेन्ट त्यो बुक 1 को मात्रै मिला छैन के? बुक 1 को पार्ट छ नि,
पार्ट गरेर छ नि। यसमा त सबै एकुरेट छ। कन्फ्युज भयो त्यो क्वेसनको त्यो प्याटर्न हेर्दै गरेको त कुन कता त्यसरी छ क्या। त्यसले नयाँ बुकमा चाहिँ कन्टेन्ट कसरी छ सोध्यो क्या।
क्वेसन सल्भ गर्न थाल्छ जेमस
छैन।
सल्भ गर्ने बित्तिकै पाउँ है एन्सरहरू चाहिँ केटा।
भन केटा हो कन्टेन्ट कस्तो छ नयाँ बुकको
अब हेरेको छैन बुक
होइन,
हामीसँग नि
हेरेको
त्यही
ल्याएकै
बुक हो
छैन।
तिमीसँग नि त्यही
प्रिन्टै
बुक हो
किन हरिसन छैन भने होइन हरिहरसन छैन
कोहीसँग
सेम छ
छैन नि
केही फरक छैन अहिलेको त
कन्टेन्टहरू
केही छैन यसमा सेम हो
मोनिटरिङ एन्ड ग्राउन्ड अपरेसन भने छैन यो च्याप्टर
हामीले
कुन हो
त्यसले छुट्टा छ त्यसले होइन त्यही सेम छ यो
लेभल 3 को क्वेसन छ नि इन्जिन मोनिटरिङ र ग्राउन्ड अपरेसन भन्ने यो
सेम हो केही फरक भएको
भन्ने
छैन
स्टार्ट हो क्या भने नै कन्फ्युजन
केही फरक भएको छैन यही किताब हो हामी त अघि त्यही बुक टु पढाएर बुक हेर्न थालेँ मैले त त्यही पुरानो बुक हेर्न थाल्यो सेम छ
कन्टेन्ट सेम हो
हटाएर त्यो लास्ट बुकमा राखेको
कन्टेन्ट नै फरक यहाँ लेखेको छ अनि त्यसले कन्टेन्ट के भनेर सोधेँ क्या कन्टेन्ट चाहिँ कसरी लेख्दा रहेछ
सेम हो
ओ खैरे आइसक्यो
Guys, back again. Yeah, busy revising there. Sounds good.
Ready then.
Give each other questions. Oh, good. Right. Okay, we'll move on a little bit. I'll finish this a little bit off, and that'll do for today. We'll just finish on this bit of recap, and then we'll crack on with some other bits tomorrow morning. So a bit of recap today, a bit of recap tomorrow morning, and then we'll pretty much finish the book tomorrow. Easy peasy, not a problem at all. A few bits I'll take a bit of time with. We're going to have reheat and compressor washing and all that sort of good stuff as well. So the last bit I'll do today is we'll do some burners and some recap, and we'll take it from there. So burners themselves, again, you'll only see these when you're inside, looking inside the borescope, using borescope equipment. You will see bits of carbon. They won't be all nice and shiny like those, unfortunately, but it gives you an idea of various types of burners and what they should look at when they're clean, but they won't always be clean. But around here, it should be nice and concentric. At least burner flare suspected. Again, it should be checked. You'll get hot spots within the combustion chamber if one's blocked or etc. Difficulties in starting, yeah, if one's blocked up, not working right, carbon buildup can cause problems. So if you have any problems with starting an engine, there's a good chance that maybe the burner's been blocked as well. Or if it's an older starter type engine, it could be the distributor weights for the fuel supply. But again, there could be many things. If it won't start, you've checked everything externally, then you go internally, then you might find there is a problem somewhere. Okay. Swirlers, again, inside some of the burners, not these ones, but you see some swirl vanes there. They can be cracked or missing, or burnt away potentially. Again, for security, you can't really check it for security because you can't really physically get in there. But certainly before you fit any, if you take them out for whatever reason, before you fit them, check them for security. But certainly once in there, you can only visually check them using a borescope equipment. All right. So again, and you're also checking for cracks. Very important. If you get a crack on the body of a burner, you see where the welds are, you know, they're weak points. And through time, they can potentially crack any where the body part is. Okay, so again, anything looks wrong, hot spots, discoloration, potential cracks, again, will need to be replaced or such like. Flame tubes and liners, well, this is what can happen if you've got hot spots. You can see evidence of hot spots here, very discoloration. And now what was on about unzipping is all these little cooling holes, okay? Again, it's not the best photograph, not very clear, but little cracks can start between these holes, and then eventually enough stress and it will just literally unzip it like a normal zip. Okay, and you see some cracks between that hole and that hole. Again, this one's obviously gone to a bit extreme. It was probably still working, but you probably got hot air coming out of there, going. You probably got an LP cooling overheat detection as well. Again, more hot spots. So again, potential burner not doing its job right. The holes in the flame tubes are often starting points. They're a weak point. A hole anywhere is a weak point, even though it's an intentional hole, like the cooling holes here and the small ones there. They are weak points, and they will potentially start to crack at some point. Again, limitations. You're allowed so many cracks at a certain amount of area. So again, check limitations in your manual. Cracks, again, circumferential cracks are usually more serious than actual cracks. Again, because as I can say, it can unzip itself. Distortion, wiggle strips, corrugate spaces, the cooling holes, again, all that good stuff. any sort of discoloration is a sign of something's not quite right. Anything that's distorted, again, we're using the light of the borescope equipment, can give you a shadow, so you might find shadows where there shouldn't be shadows. But anything that doesn't look right, it probably isn't right. Holes can be caused in two ways. Cracks can cause pieces to lift away and break off. Like you can see here, you can see there's a crack been there and just unzipped itself. The stress has made it blow out. And you can see the start, this one here, as I say, you can see another crack there. So potentially this area would probably go end up like this part at some point. So it's certainly done its well. Carbon deposits are intense black, and sometimes instead they can be mistaken for holes, so it's just purely carbon. But again, if you suspect that, change the angle of your borescope equipment or get a second opinion just to make sure. Because as you're looking in there, your eyes can get a bit funny, and sometimes even getting a big screen. And with a newer type of equipment, you can plug it into the big screen, magnify it in, and that might be able to help you out as well. Lots of different ways. NGVs, well, remember they're one of the highest hot parts of the engine. Okay, apart from the combustion chamber, you've got the cooling holes, got the cooling going through there. So eventually these cooling holes will erode away and burn away as well. And some of these can actually go missing. As I said before, I went and checked an set of NGVs, and 3/4 of the blades were missing. Okay, they lots and lots of segments that just burnt away, and all was left was the stubs. Okay, so take your time with these, and this is the sort of erosion you might come across. All right, so again, that's going to cause aerodynamic losses and disturbance with the air onto airflow in the turbine, which could cause a bit of vibration, and eventually this could actually break away. And where's that going to break away and go? It's going to hit the turbine. All right, so if you're lucky, small bits at a time, and the turbines can chew them up and spit them out, that's fine. But if there's no cooling protection, that hot gas is just going to burn it away. All right, so the cooling holes won't actually do their job anymore. But because of the low cycle fatigue, they're cold, they're hot, they're cold, they're hot, you know, they eventually will crack and get worse. You'll find usual nicks and dents, possibly. There shouldn't really be nicks and dents because there should be nothing going through the combustion chamber that should affect it by the hot gas. But a small bit of fog might have broken off something through the cooling air, you know, from the compressor side of things, and gone through the bypass air, and the bypass air going into the cooling NGVs and maybe going up through the blades themselves. NGVs, I say, are subject to extreme gas temperatures, and you can only do check them with endoscopes, borescopes. Sometimes it's impossible to actually check all the NGVs, but nowadays with the flexible tubes, certainly with the old rigid tubes, it's quite hard to get every NGV. But with the IPEX ones, you can actually see it all the way around. You can actually get your tube all the way around. You get so far, and you go to the other side of the engine, and go back on the other side. Oops, dropping that there. And so nowadays you can pretty much see everything. When I went to check, it was a turbine I was going to check, and my probe went in and just happened to be facing the NGVs. Now, we didn't really need to check the NGVs, it was just the turbine we were checking. But because I looked in, it was facing NGVs, and I noticed they were all missing, I had to highlight it. You know, if you go to your car, you've got a flat tyre, you don't leave your flat tyre, you go and sort it out. So there's a bit of an argument when I was looking at that. Well, just by accident, and I found them missing, so they need sorted out. So we had to get concession from the manufacturer to leave the engine until it was coming out within about, I think it was coming out in about 50 hours time anyway. So normally it wouldn't bother them, but 3/4 of the NGVs were missing. Well, if the NGVs are missing, they're not doing their job. Yeah? What's the purpose of an NGV?
To guide the hot air to turbine.
Yeah, and accelerate the gas as well. So if a lot of them are missing, they're not doing the job. Yeah. So a big argument with the bosses there, and eventually won, thankfully. But it was safety. If the NGV totally failed, then the centre part would have hit the turbine, broken the turbine, and the engine would have blown up. So it was it was quite an essential part. Yeah, again as well, if it's looking okay, looking for discoloration, cracks, again, you'll get cracks propagating along the edges there, and also look at the trailing edges. The trailings are very thin, and you get cracks sort of starting up and going up here, and eventually join up to the holes and dissipate as well. So again, take your time. Burn erosion is common, and again, tearing occurs on trailing edges. It looks like you're tearing a bit of paper, and that's the sort of effect you'll get. So again, take your time with them. Turbine blades, there we go. Nice little profile shot for you there. Okay, what shape is that making? More than that, you'll see it better than that one. What shape do we call that?
Impulse reaction.
Impulse reaction, yeah. Good old Nike tick or Usain Bolt, yeah. And there you see the turbine blades with shrouds on them as well. Okay, so these are obviously brand new. They'll never be that colour when you see them. They'll be more like this. But we've found a crack. Now, that is only going to get one way. It's going to get worse. So that would be an engine rejection. Okay, there's no way you can fix that. You wouldn't even monitor that. You would, if you found that in a blade, that's an instant rejection. If somebody said to you, I'll be okay, no. Because what's going to happen? Well, that's a stress point. That blade comes off. Now, if that's an HP turbine, that blade will snap off. And if it's a triple spool, okay, it will break the IP turbine. Then that will break, and that will break the LP turbine. So a lot of damage could potentially happen. If it's an LP turbine, bad enough, it's still an engine rejection. Okay. Again, you might be able to access the HP and IP from borescope inspection, the endoscope. So again, when you're viewing the airfrost surface of the blades, the end of the probe located between the blades must be withdrawn prior to engine rotation. So again, be very careful because you have to rotate the turbine using the gearbox to HP spool or an IP tool for the intermediate turbine. Nice and slow. Make sure get to rotate first before you put the probe in. You'll be able through experience know how far to put it in. If you put it too far in, what can happen is you'll get the probe stuck in the tip here. I do have a photograph from the PowerPoint, and it's quite embarrassing if you try and get it back out. If you can't get it back out, unfortunately, that's an engine removal. So what was a serviceable engine, you've now made unserviceable. Okay, so please take your time. Again, you'll be fully trained on these. Turbine blades, again, some of the same sort of damage as NGVs. Limits are more stringent, so NGVs can take more damage, not as much as I saw in that previous one, but certainly the turbine blades do not allow as much damage we would find in NGV. Cracks tend to appear along the leading edge, just like we've got there. So a good photograph there. Erosion is normal, and to a point where the wear away thinning off, and that will distort the airflow as well. You will get deposits sometimes, and so again, check the colour of the deposits. You know, we've had occasion where the aircraft were flying through volcanic ash with Iceland back in, I think it was 2009, 2010. The volcano erupted in Iceland, and the cloud of smoke was coming towards Scotland, and we had to check the aircraft every flight for potential ash injection, because the ash would melt and block the cooling holes, etc. And we did find some. We did find actually some, to a point where to reject some engines. So take your time checking them. Any damage? Yeah, it's nice and easy when it's out, but obviously when you're looking at a borescope equipment, would you bother recording this? No, because you'd be recording it because the turbine is broken. Every single blade has got damage, so you wouldn't have to say how many blades, but if you did find one or two, you would say blade number 2, 3, and 4 found missing from, you know, you might find a mark on the disc or something, or an indication of the route, but usually turbine blades, you won't see any numbers on them. You'll just have to say times 3 blades missing, or you might find that the top spot from the turbine, the LP turbine from the back. HP turbine is a bit harder. You just have to find a mark that might be able to give you an idea. Okay, but certainly this whole turbine is completely trashed. Okay, every single blade has got damage on it. So what's happened? Maybe this blade's come out, or this blade's come out, and then they've disappeared and trashed the edge of the rest of them. Okay, so it's pretty much on its end. Okay, again, anything you find, whether it's LP turbine, compressors, record the position, how many, what type of damage it is, put your date on it, time on it, and record on the job card. And then obviously something like that's very extreme, that would be engine removal. But if it's just a tiny little bit missing, you might be within limits. Again, you have to check the limits according to the manufacturer's instructions and take it from there. Okay, so just about there.
Excuse me, sir.
Yeah.
This is the HP turbine?
That's a turbine, yeah.
HP turbine or LP turbine?
That's probably, looks like an HP turbine. The size of that one, yeah. HP turbine.
And then this HP turbine is, if there is damage, it will hit the LP turbine or not?
Yeah, but what, sorry?
if the HP turbine is damaged, the blade of the HP turbine is damaged,
Yeah.
then it hit the HP turbine or not?
Yeah, it might hit the. If it depends if that's a twin spool or triple spool. If that was a triple spool, that will come out and hit the IP turbine. Then that will hit the LP turbine. So it'll probably take 2 turbines out. So those blades have come off, gone back away, and probably broken the other turbines, because the HP1 was the inside, then you've got the IP turbine and then the LP turbine. Yeah, HP, IP, LP, or HP, LP. So yeah, that's definitely one of the, looks like the HP turbine. Might be an IP turbine, can't tell exactly, but look at the size of blades, I'd probably say HP turbine. I'll try and maybe find information for that. On the turbine, there's a disc. You can actually see the seals, the air seals. Yeah, around there. And there's the main sort of face of the shaft. So by the size of that, I would say that's an HP turbine. Look at the size of it. Okay, but yeah, it's broken. I'm not going to run that one again. All right. But any turbine, any compressor, any damage you find, record it. And even if it's out of limits, you need to record it. So it will go for, they might start finding a lot of the same engines are starting to get the same damage for whatever reason. This might have been gone past into its tertiary life. You know, with the tertiary point of the creep, it might have gone past that, or it's been overheated. There's a lot of discoloration there. Saying that, discoloration isn't abnormal. Looking at that colour there, just in my experience, that's the sort of standard colour you come across. But certainly, or something's hit it. Maybe something's come through and actually hit the turbine blades. Yeah, and taken it out, gone around the inside. Enough stress on these ones to break them off, or it could be a faulty blade when it's been made. Again, without the information, I can't really say, but certainly something's hit it, or maybe this one's come off and trashed the blades and taken some out with them. Okay, but it's damaged every single one. The fact they're all damaged, okay, is indicative that something's either hit it or expanded so much that the creep has actually hit the shroud around it. But looking at that, I think someone's probably hit it by looking at it. Okay. It all depends. It just really depends on the damage you get. But it must be recorded, even if it's out of limits. Record on the job card. In this case, we found 4 blades missing. Numbers 2, 3, and 4 together. Blade 12. However, they've numbered that. We've got 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. But again, wherever you number that from, you probably wouldn't find a number on the actual blades. You tend not to find that. All you can use as a reference is maybe a point on the disc, or you might find a mark, you know, maybe a hot point or a hot spot, and use that as a reference point. And then you'll be able to know how many turbine blades are on there. Okay. But if in doubt, something like that, just put how much quantity of blades found to be damaged. That's what I used to do. We'd say maybe 4 blades found damaged, 2 times on leading edge, 1 on trailing edge, found to be within limits. So if you do find damage and it's within limits, you write that in the job card. 1 times blade found to have erosion of leading edge, found to be within limits. 1 times blade found to have tear of trailing edge, found to be out of limits, turbine to be rejected or engine to be replaced. Okay, so that leaves an open entry in the job card for the work to continue. Okay, so make sure it's an open entry so that the job card doesn't get finished off. Again, you'll learn more about that as you actually do it. Right, last one for today will be the heavy landings. I think we'll do that
blade
one.
turbine.
What, sorry?
Turbine blade with limited damage also require boroscope inspection. Yeah. I mean, as I say, that's why you don't be able to check an HP or an IP with a boroscope. The LP you can see from the back by looking at the exhaust, but certain HP you can only get in there with looking at your boroscope. This has also been taken out. They've inspected the engine, they've found the damage, they've disassembled the engine, and they've put the turbine on a stand. Okay, and actually, if you look at the bottom there, I think that might be the LP turbine still attached to it, and all the blades are missing because this bit's come off and trashed the turbine behind. And I've seen that before. I've seen an IP turbine blade, only 1 blade, a little bit come off, a clean break, and as it's gone back, it's hit the LP turbine and taken all the blades out. All you've been left with is little stubs like that. Okay, so 1 little snap. Now, what might have happened, it might have been a heavy landing, and that blade, the creep is maybe just on the edge, it's just touched the casing,
snapped a little bit off, and that one little bit spun out and took all the blades out. Okay, because we've had the engine came into us. We didn't know what happened. We've been told there was vibration in the engine, been rejected because of vibration, and that was all much we got told. So we looked at the front of the engine. There was a tiny little nick on one of the blades. Okay, went to the back of the engine, and the LP turbine was missing. It's just all the blades gone. So as we started stripping the engine down, we found the IP turbine blade had snapped off. So possibly that little nick on the compressor blade might have been a little bit of FOD. That might go down the bypass and then hit the IP turbine and snapped a little bit off, and then that bit snapped all the blades off. So it just shows you the chain effect of what could be a small bit at the front, can be a lot of damage at the back. All right. Okay, let's move on to the last bit for today. Is engine inspection after a heavy landing, and hopefully never fly like that. Okay. Okay, so engine inspection after heavy landing.
Crosswind.
Say again.
Crosswind landing.
Yeah, crosswind landing. Yeah, you come in heavy, and I've had that a few times myself. Gets you. I've only been in one flight, but everybody's done a round of applause to the pilot because we landed safely. I did a bit of that a few years ago. Makes you think. So yeah, if you get a heavy landing, you're going to put a lot of load onto the engine. So the engine's going to bounce. You know, the shafts are going to bounce on the bearings. So potentially you could damage the bearings. You might have to do checks on the chips, oil systems, lots of different things. Check fuel range control, the movements, the throttle movements, and all, especially if it's an older style where it's all connection rods and cables. Fly-by-wire, well, it's very hard to check that. But certainly for the older style, you have to check free movement of the controls. Check for bows in the members. Okay, if it's overstressed, fuse pins could be stressed. You might have to do NDT checks. Lots and lots bolts for damage. Do a physical, put your hand on the LP turbine and spin, well, or the LP compressor, sorry. Spin the compressor. Does it sound right? Does it feel right? And then even actually hand turn the gearbox to check the HP turbine. And if you've got a triple spool, get a tool to check the IP turbine as well, an IP spool. Make sure everything is free to rotate, because if the bearing's been damaged, it's going to feel notchy and gritty, not very well at all. You'll check for fuel, oil and hydraulic leaks, because it's sudden pressure can also cause problems as well. Prop shafts, shot loading, the corns with. So if it's a propeller, again, the propeller can bounce on the reduction gearbox. Check your, I said already, check your chips, your filters, internal borescopes if required. It might do that as part of standard procedure, certainly for us it was. And if you find no damage, now you're probably going to do a ground run and check that everything is operating correctly. Okay. So you imagine a lot of side load as well as the vertical load hitting there. There's a lot of side load as well. Okay. So that's pretty much that one for there. But again, you follow your maintenance manual, it will tell exactly what you need to check and the severity. I asked the pilot what sort of how heavy a landing was it. There'll be aircraft checks as well. There'll be undercarriage checks, brake checks, as well as the engine checks. But purely from an engine perspective, bearings, oil systems, chips, internal, external, visual and internal inspection. And if you're lucky enough to get one of these ones, a lightning strike, well, aircraft are designed to withstand lightning strikes. That's designed to dissipate the power. You might hear something getting stricken in an aircraft. This one's a bit unfortunate because you can see here, we've got a wheel fire. So it's landed, hit by electrical storm, and he's unlucky to have a wheel fire. So with that one, I wouldn't worry too much about the engine initially. I'd be worried about actually stopping the aircraft. Okay, so yeah, lightning strikes can cause problems. Obviously, the power supply going through. Examine external surfaces for burn marks, any signs of it. If you do find a track, depends where the lightning's hit the aircraft, it usually dissipates through the fins and specific zones of the aircraft. So again, you'll be checking the main bearings. You'll be checking the oil system for contamination, cooking of the oil, soap sampling if required, send away the chips to be tested. And again, checks should be repeated periodically for a specified number of hours. So let's say, for example, your magnetic chips were tested normally to normal flying every 100 hours. Well, after a lightning strike, they might reduce the hours to maybe 50 or 20 hours, a quick check to make sure everything's okay. And then once everything's still okay, then they'll put the hours back up to normal hours, providing everything's okay. Oil systems, again, they might even drain it, replace it. Again, it all depends on the manufacturing instruction for that specific aircraft. Okay, and that is about it for there. So just double check where I am. Repairs will sort out. Yeah. Okay. How are we doing for time? It's 4 o'clock there. So that's as far as I'm going to go today. We've got a small bit left for repairs, but again, we'll finish off tomorrow morning because I'd like to speak a bit more about that rather than rush it for today. So we'll just a couple of bit of recaps. Okay. Most of it is self-explanatory. This section is quite self-explanatory. Have a nice read through it. Follow the maintenance procedure. You can't go wrong. Yeah. Record any damage you find, good or bad. Even if you don't find damage, you would still write a job card, HP turbine, inspect it in accordance with the manual, whatever the number is, and turbine found to be serviceable. Okay. They don't tend to put what's called NFF now, no faults found. They don't like using NFF now because the N, depending how you write it, looks very close to off. Okay, so they tend to write, if you find nothing, just put found to be serviceable. Again, when you're doing paperwork, keep it short, sharp, and to the point. Don't write massive stories, but make sure you have all the relevant information in there. All right. Yeah, I mentioned just before break about the blanks for the borescope or the endoscope access points. Again, we're using many different size, specific anti-seize compounds. Sometimes it's just normal engine oil, just a little smear of engine oil on the threads. That's usually enough. But again, double check with your maintenance manual what you're meant to put on there. And don't mix them up, because mix them up, it can cook and it gets a sort of gritty type thing, can cause a lot of problems. Okay, if you're away to do an endoscope of an engine, safety, what would you do first? If you've had an engine run and you need to go and check internally, maybe had a heavy landing, so the aircraft just landed, had a heavy landing, what would you do before you go inspect it? So think safety. So aircraft's landed, been reported as a heavy landing, or even a lightning strike that we've got there on the screen. So what would you do before you go and get your borescope and go and put it in the engine?
We have to first ground.
Yeah, you'd have to obviously chalk it and ground it and all that sort of thing. Depending where the aircraft is, if it's a heavy, a lightning strike, I would certainly wouldn't be working outside. Okay, if there's lightning going on there, you'd certainly get the aircraft back in a hangar or somewhere suitable, or wait for the thunderstorm. I wouldn't be checking it outside, that's for sure. I have a colleague many years ago who got hit. Now they say you never get hit by lightning twice. My colleague did get hit by lightning twice. He was put in an air lead. He connected to the on the ground to the aircraft. He was connected on the ground, and just as he put the air lead on the ground, he got zapped, hit the air lead, so he got thrown to one side. And he was okay. He got a couple of minor burns, and a year later, he got hit again by lightning. Very, very lucky. He's okay. He survived, but you never expect to be hit by lightning twice. But he certainly did. But yeah, if you're in an environment like that outside, we would wait till suitable weather, go and check it, or get the aircraft back in one of the hangars, or under cover at least, and check it. But obviously, the aircraft just landed. Engine is very hot, so open the cowling doors, let the engine cool down, and you can certainly do things like the LP rotation, maybe spin the LP fan. Is the LP spool spinning okay? Have a visual inspection outside as the engine's cooling down. Look in the fan, look at the turbine, check for any signs of leakage, because something's electrical strike that can cause things to blow. Any visual indication from outside as the engine's cooling down. Once the engine's cooled down suitably enough, then if you're happy with external inspections, then you go and do an endoscope or a borescope inspection. So remove the plugs appropriately, get your equipment out there, have a look inside, have a safety person, and go through the motions as accordance with the manual. Okay, and keep safe. That's the main thing. Okay, if you're using a rigid borescope, there was 4 types of views. Okay, this is the older type, the rigid ones. But again, we still use them today because sometimes actually get a better indication. So 4 types of views. Anybody remember the 4 types?
Straight, lateral, oblique, retro.
Yeah, good. Yeah, retro, oblique, lateral, and straight. Good. Oil system. Let's see. Yeah, as I put there, one of the most common reasons for discrepancies in oil consumption is unfortunately engineers not putting the right amount in, or they forgot how much they put in. They'll put a rough estimate, but that becomes obvious. As I say, you've seen the graph. There'll be a big spike either down the way or up the way. Somebody just put a random figure in there. They forgot what to do. So again, when you're doing replenishments, fuels, obviously make a note of all the replenishments and that sort of thing. But again, synthetic oils, very toxic, so be very careful when you're using them. Keep yourself clean. If you were to change the oil, how would you do that?
First, we have to completely drain.
Yeah.
Partially refilled with the new oil.
Yeah.
And then engine should run for the 15 minutes.
Good. And then
the system should then drain again and then refill with completely.
Yeah. Good. Yeah. You don't need to install the oil, so we can drain it fully, put some in, warm it up, and then drain what's there, and then replenish with the clean stuff. Good. All right. If you were looking at the back of the engine, you're looking at the LP turbine, you're checking for discoloration, and you found some deposits there, and they were sort of bright blue or golden speckle, what would that be indicating? What type of material?
If it is golden blue, then titanium.
Yeah, good. For aluminium?
White and silver.
White and silver, good. Easy peasy. This is a nice easy section, yeah? Compressor damage can be generally assessed as 3 types of damage. What were they?
Superficial
impact.
Repairable.
Yeah. And repairable, yeah. So superficial, again, damage a small dent, which is standard normal. Impact damage, as it sounds. Repairable damage, minor, grit you can blend out. What we'll look at tomorrow, we'll look at how we can blend a blade in situ without taking the blade out, providing some within limits. Good. That's easy. Not giving you easy ones. Maintenance, just have a run through. Oh yeah. What's the purpose of flat rating?
Is given by the manufacturer the maximum thrust amount to be achieved in certain temperature.
Yeah. That's it. Yeah, flat rating allows the engine to produce constant rate of thrust over a wide range of ambient temperatures without working the engine harder than necessary. In other words, guaranteed amount of thrust depending on where you are within that envelope. Good.
It's computed by FedEx, right?
Yes. Yeah, you can tweak that. We did something with the Tornado aircraft with the DECU, same as a FedEx, but called the DECU. And we actually derated, we actually changed the flat rating of the engine. We actually call what was called derating. So we lowered that shape there, the ceiling, the flat part, the flat rating, we actually lowered that a little bit to allow the engine to survive a bit longer because all these jets we used to work on now out of service. So we're trying to keep the engine as long as possible. So Rolls-Royce, who manufacture engines, said we need to derate them just to give them a bit more length of time in service. So we actually reduced that flat rating a little bit and we tweaked the engines back. So they lost a little bit of thrust, negligible, it's hardly anything. It just gave a few more hours worth for that engine. Okay, thinking about horsepower, we've got indicated, brake and shaft horsepower. What is shaft horsepower?
Power delivered by the propeller shaft?
Yeah, the rotors, yeah. And what's a typical percentage loss?
10?
Yeah, 10%, good. What is indicated horsepower?
Theoretical power.
Theoretical, that's it. Good. Nice and easy, Okay, that one's Okay, I'm just about there. That's fine. Yeah, ones to read over is the engine performance. With reference to engine performance, you've got thermal efficiency and propulsive efficiency. Thermal efficiency was broken down into two more efficiencies. What were they?
Indicated thermal efficiency and brake thermal efficiency.
Good, yeah, indicated and brake. Yeah, indicated again being sort of theoretical, but assumes no mechanical losses. And again, the brake one, comparison when the heat obtained from the fuel velocity of the gases leaving the engine. So again, things like gearboxes attached. Good. Right. Okay, doke. What time is it? That's close enough, I think. We've got 5 minutes to go. So any questions from yourselves, gentlemen? I'm waiting for the classic phrase.
Good night.
That's the one. Okay, folks, if you've no more questions, thank you very much. We shall see you tomorrow again, and we'll finish off the book. We'll do a bit of recap, a little bit quicker. Start again, a quick bit of recap in the morning. Then we'll finish off the book, and we'll start the full revision again. We'll start with book 4, obviously, then we'll work way back to book 1, and then on Friday we'll do the 100 questions revision as well. Okay, folks. See you tomorrow.
Okay.
Sleep well. All the best.
Have a good day.
Thank you. And yourself. A good night.
Good night.
के छ केटा हो खबर?